There are a couple of situations where there would be no cis or trans designation for alkenes. And the first one is when the double bond is occurring at the first or last carbon. Here is an example. This structure here, there is no cis or trans. Now, if you look at this right away, you can notice that there is no chair shape. Remember that chair shapes look like this. And you cannot see a boat shape either. Okay, just simply not there. To see why that is, let's draw the condensed structure. So I have my carbon, carbon. This is my double right there. This is carbon 1, carbon 2, and I've just drawn them here, 1 and 2. Okay. Then we have 3, 4, 5, 6 carbons left. And I'm just going to draw them really condensed to save some space and some time. So there we go. 1, 2, 3, 4, 5, and 6. Okay. When we look at this, right away, we see that we have a branch here on the bottom side of that double bond, but there is no carbon branch anywhere else. So since there's no other branch to compare this branch to, there's no way we can assign cis or trans. Okay, so this molecule would simply be called 1-hexene. Let's look at another example. Another case where you would expect no cis or trans designation is if the branches on both sides of that double bond are equal. So when we look at this particular structure, here is our double plane, and we see that there's 4 of these branches attached to it, but they're all of the same value. They're all 2 carbons strong, 2 carbons large. So then we cannot choose 2 branches to compare whether they're on the same side of the double or the opposite sides. If I would draw that in the condensed form, the structure will look like this. Like so. Hopefully you can convince yourself that this is indeed the corresponding condensed structure. And we see that if we were to look across that double, our branches are of equal value all around, so there's no way to choose 2 of them to compare whether they're on opposite sides or on the same side. This structure here would be called 3,4-diethyl 3-hexene. 3,4 because if we start numbering from 1, 2, 3, 3 is when that first double occurs, and at position 3 we have a ethyl. At position 4 we have an ethyl, and then 5 and 6 for hexene. For this particular structure, you can count the carbon chain starting from any carbon, because this molecule is perfectly symmetrical. You could start up here and you would still get 3,4-diethyl 3-hexene. Alright. Another situation where cis and trans cannot be assigned is if the alkene is shown to you in a condensed structure. For example, CH3, CH2, CH2, CH, CH, CH2, CH3. First of all, when you see this, where is that double? Hopefully you are going to say right here, because we're missing H's, so that's where the unsaturation is taking place. Now when you look at that region, you can't tell if the branches that are attached to that double are pointing upwards or downwards, because we've drawn it in the condensed form. So because of that, there's no way for you to tell, so you would not assign cis or trans. We would label this from the right side to give the double bond the smallest number possible, which is 3. There's 7 carbons, so this would be called 3-heptene. Okay, here's another one. Oops. CH3, CH. This is also called a condensed structure, but it's slightly uncondensed because it's showing you each bond between the carbons. Okay, here we go. The double bond is in this region here, but once again, when you look at the branches that flank it, so this portion here and this portion here, you can't tell whether the two sides are pointing upwards or downwards, and so we would ignore the cis and trans assignment. This would just be called 2-methyl 3-hexene. Okay, 2-methyl because 1, 2, 3, 4, 5, and 6. We label this on the left side so that the methyl group gets a lower number and the double bond gets a 3. If you were to go from the right hand side, the double bond would get 3 as well. However, your methyl group will be attached on carbon 5, which is not ideal because it's a big number. Okay. The final situation where you cannot assign cis and trans is when the alkene is cyclic. Now again, cyclic means circle. Let's draw a cyclic alkene. Here's an example of one right there. Now, is it possible for that double bond to be trans? Now remember that this is a ring. All rings, they're going to be like this shape, this boat shape, right? In other words, they're always going to be cis. So we cannot assign cis and trans because there simply isn't a need to. It would be redundant to call all the rings cis. So we don't do that. When we number the thing, the double bond takes priority. So we would just call double bond 1. And if it takes priority, it's automatically assigned 1. It would also be redundant to write 1. So we ignore that number. This would just be called cyclohex because it's a six-membered ring. And instead of hexane, we're going to write hexene, cyclohexene. If you have more than one double bond in a ring, like this one, here is how you would number them off. Obviously, one of them is going to be 1 to keep the numbers low. Now, where you put 2 is important. The rule for numbering alkenes in a cyclic fashion is that we always number across the double bond. In other words, if you're going to call that particular carbon 1, 2 must be the receiving carbon at the other end of that double. So our numbering system is 1, 2, 3, 4, 5, and 6. It would be incorrect to go 1 and put 2 here because we see that the other end of that double bond, that carbon there, you've ignored it. So it's not correct to label the 2 at the carbon without double bond. You have to always label across. Okay, so that actually simplifies things because we see that our double bond's appearing at 1 and the next time it appears is at 4. So this is called 1,4 cyclohexadiene. Once again, that di prefix is appearing right before the thing that it's applied to, which is the ene, which stands for a double bond. Okay, 1,4 cyclohexadiene. In our final example here, let's add some branches. The rules stay the same. The double bond gets priority. We have two options. We can label this one 1 or this one 1. Let's try both and see which method gets us a lower number set. If we call this one 1, this one must be 2. Again, we're labeling across the bond here. 1, 2, 3, 4, and 5. So we see that our numbering is going to be 4 and 5 for our branches. The other way we could go is we can go 1, 2, 3, 4, and 5. Which way are we going to go? We are going to go counterclockwise. Counterclockwise gets us numbers 1 for the double, 3 and 4 for the branches. If we went the other way, they would have been assigned 4 and 5. Okay, so I'm going to erase that and just put on the correct numbering system on for your notes. That's nice and clean. Start over. Here we go. So we're going to go 1, 2, 3, 4, and 5. This would be called, again, alphabetical order, 3, ethyl for methyl, followed by our double bond. Now again, we have one double. Writing one would be redundant. We know exactly where it is. It's automatic number one. So actually, we're quite finished here. It's 3-ethyl 4-methyl cyclopentene.